Hello everyone. Thank you for your interest in our research. I am Jaideep Saha, a PhD student from the National University of Singapore, and today I am going to present our paper titled A Bidirectional Matrix-Based AC-DC Dual Active Bridge for Modular Solid-State Transformers. So the agenda of the presentation will have a brief introduction about the solid-state transformer technology and our focus. Then I will explain the topology and modulation scheme of our proposed solid-state transformer scheme. Then I will talk about the small signal model so required. And lastly, I will show the simulation results, experimental prototype, and some of the scaled down experimental results, followed by the conclusion. So introducing the concept of solid-state transformers, I would say that it is a power electronic topology with galvanic isolation, and for grid-connected applications, it is often multi-level. So the solid-state transformer technology is referred to as smart transformers, power electronic transformers, and by various other names by different R&D groups all over the world. And here I have shown the topology of the conventional three-stage modular solid-state transformer, which is often referred to as the cascaded modular solid-state transformer, or the CMSST. So here you can see that the conversion is first from the medium voltage AC grid to the low voltage DC bus, and then the low voltage DC bus is interfacing with the low voltage AC grid using a tie converter. So the conversion is from medium voltage AC to medium voltage DC, then medium voltage DC to low voltage DC, and then to the low voltage AC. You can also see that the distributed energy sources and distributed energy storage is being integrated with the low voltage DC bus using the converters dedicated for them. So this is the common microgrid architecture, or let's say a hybrid microgrid architecture that you would see. Now let us concentrate on the medium voltage AC to the low voltage DC conversion of the solid state transformer, where you can see that the architecture is such that in the front end the submodules are connected in series towards the medium voltage AC grid and in parallel towards the LVDC bus. So this architecture is very commonly known as the input series output parallel kind of configuration, or the ISOP configuration. Now, if we concentrate on the AC to DC submodule of the MVAC to LVDC conversion, we can see that it has 12 switches, of course. That is, you can see that there are 3 H bridges. And the first stage of conversion is the rectification stage, which is followed by a bulk electrolytic capacitor, which filters out the second harmonic component. Then you have the DC-DC dual active bridge with a medium frequency isolation. Also, it should be noted that the 3-phase modules, the red, yellow, and blue, they are interleaved to be connected in interleaved fashion at the LVDC bus. Okay, so we move on to some of the improvements over this conventional submodule, which has 2-stage conversion. First up, we have a direct improvement over the previous submodule by eliminating the bulky electrolytic capacitor after the rectification stage. So what is being done is the dual active bridge is being controlled in such a manner that the current I1 is controlled to be proportional to V1, that is the rectified voltage just after the rectification stage. And the second harmonic ripple is being transferred towards the back end, and the interleaved operation of the 3-phase modules would then cancel the second harmonic ripple, as the second harmonic ripple from the three different phases are at 120-degree phase shift, and they get added up to get cancelled. And as a result of the control, you would have a very nice sinusoidal current at the grid side. So the improvement, I would say, is that the bulky electrolytic capacitor could be avoided, as the second harmonic components get cancelled, and you just have the switching frequency harmonic to be filtered, which can be easily done with the quite power dense film capacitors. However, the number of switches remain the same as the conventional topology. Then we see the switch solid state transformers submodule, where they have a front end AC to rectified AC um, isolated front end conversion stage, which has a medium frequency isolation, followed by the rectified AC to DC boost converter stage. Here the boost converter has all the control, and it is controlled in such a manner that the I2, the current here, is proportional to the rectified AC voltage. Um, so you can see here that it has the similar kind of advantage, where the ripple is being transferred from uh, having a stiff second harmonic filter to the DC side, so that the interleaved operation could cancel the second harmonic ripple, and you're left with only the switching frequency ripple. Yeah. So here there is an additional improvement where the number of switches are lower. So compared to the 12 here, you'll have only 10 here. So what we propose is improvement or further improvement over the switch solid state transformer submodule, and we have eliminated the DC or the rectified AC to DC boost converter stage, and we just have a half bridge matrix based AC-DC submodule out here, where we control the current through the leakage inductor of the medium frequency transformer, and thus have a sinusoidal current in the primary side. So now our concentration will be only on the matrix-based AC-DC dual active bridge submodule, where you can see that there's a matrix-based half bridge at the front end and the H bridge at the back end. And you have the medium frequency transformer, whose leakage inductance is suitably designed for the required power transfer. We have the BP and the VS, which are respectively the pulses that are impinged by the matrix side as well as the secondary side H bridge. And here we can see the possible modes of operation, where the red signal is, or the red waveform is the waveform BP, that is the square waveform that is being generated by the half bridge matrix converter, and the blue waveform is the pulse that is being generated by the H bridge, and both of these signals are being separated by equivalently the leakage inductor of the medium frequency transformer, which then has the current IP. So we can have these three possible modes of modulation, where for mode 1 we can see that the pulse generated by the secondary side is within the primary side square waveform, whereas for mode 2 the pulse is partially secondary side pulse is partially outside, and for mode 3 the secondary side pulse is completely outside. Now we have carried out optimization for the design of the solid state transformer submodule, and we have found that the optimal AC side voltage would be 945 volt peak using 1700 volt devices with a utilization factor of about 0.55, and the DC side voltage would be 1800 volts with 1200 volt devices, and thus the power per submodule for the considered example of a three-phase 1 MVA solid-state transformer would be 17.55 kilowatt, and the switching frequency optimally should be within the 10 to 20 kilohertz range. And here we found that for this kind of optimal parameters, mode 1 is the chosen modulation for the steady state operation, because that is where you can kind of passively operate with a fixed switching frequency, and it is quite easy. Now, there are a few things that I would like to highlight. So here, the T is the pulse width of the secondary side waveform, which can be controlled, and phi is the phase shift. So the primary side, it is a half bridge, so you really do not have any control over the pulse width. So basically this T is being modulated sinusoidally, and it gets its pulse width from the sinusoidal modulation scheme, or the sinusoidal modulation index, I would say. And the phi is being controlled using the control system, or even if it is in open loop, we give a kind of constant phi, or pre-designed phi, so that we can have the desired power transfer. Now, coming to the small signal model part, we have amended slightly the matrix-based AC-DC DAB submodule scheme to simplify it a bit more for the sake of model generation. And from the model, we have done the large signal modeling, and then the average large signal modeling. And we have separated out the steady state part and the small signal parts. And from there, I would just show here the small signal model. You can see the detailed derivation in the paper. And after that, we have derived some of the important transfer functions that would be required for designing the control system. That is, first is the control parameter, that is the phi to the output voltage. Uh, and we have shown the Bode plot of the same. Then we have the control parameter phi to the input current and the subsequent Bode plot. Then we have the input current to the output voltage, or the transfer impedance, and the Bode plot of the same. Coming to the simulation part, we have simulated the actual parameters that would have existed in a 1 MVA solid state transformer. That the submodule power rating would be about 17.6 kilowatt, and we have taken the grid side AC voltage and grid side DC voltage, as I have explained to you, the optimal parameters, and the switching frequency is kept 20 kilohertz for our simulation. And we can see here the primary and secondary side voltages across the medium frequency transformer in mode 1, and the leakage inductors voltage and current as they would be due to the pulses from both the sides, and then the current through the medium frequency transformer's leakage inductance. Also, I've shown here the current through the matrix switch and the gating signal. So here you can basically capture the waveforms that are concerned with the power transfer through the MFT according to the design modulation scheme. Okay, so there is another merit of this topology, where the voltage ripple across each of the capacitor leg capacitors, that is C1 and C2, they can have a cancellation by default, as you can see in this figure here. So as they are capacitors in series, they would get added up to cancel some of the ripple, to reduce the ripple by about 40%. And yeah, so you can have smaller capacitance there for the capacitor leg as the ripple has reduced. And here we show the grid side voltage and current, where the current is seen to have a superior sinusoidal input power quality, and the current through the 4-quadrant switch can be seen here if you're interested. So here we have the experimental prototype that we have designed, and here you can basically see one of the submodules. And we can say this is a scaled down experimental prototype. So it is designed for 3.5 kilowatt, but presently we are operating it at 2 kilowatt, and hence presently we have a power density of about 2 kilowatt per liter, and that is quite competitive, I would say, compared to the other topologies of solid state transform, and obviously better than the conventional CMSST, whose typical power density would be around 1.5 to 1.7 kilowatt per liter. And here we have the laboratory level experimental results. So you can see that we have scaled down both the primary side voltage and current as well as the DC voltage by a factor of 5, so that we can have a scaled down verification of whatever we have proposed in the modulation scheme. So basically here the logic goes like this. So as the phi 2 is negative, therefore we cannot operate it, or it doesn't make any sense mathematically to operate in the mode 2. So basically you can see that D2 is 0. So we have phi 1 and D1 which are positive, and thus the experimental setup is being operated exclusively in mode 1, as phi 2 is throughout negative. And you can see that there is a very good input side power quality with the AC current being quite sinusoidal. So coming to the conclusions, we have this proposed matrix-based AC/DC dual active bridge submodule, which is an improvement over the Swiss solid-state transformer. The suitable steady-state modulation scheme has been identified through an extensive study for a three-phase 1 MVA solid-state transformer example. Also, we have done the suitable modeling required for our proposed topology and modulation scheme, and we have come up with the small signal model of the matrix-based AC/DC dual active bridge submodule. And we have also provided the Bode plots of the relevant transfer functions that might be useful for control system design. We have shown the open loop simulation results of the 17.55 kilowatt submodules that validate our proposed modulation scheme, and also it shows the merits of the proposed submodule topology, and it is a holistic discussion of all the possibilities out there. And we have shown the scaled down experimental prototype and the experimental results at 1/5 of the actual voltage and current. And I think that is a very good validation of whatever we have proposed till now. And as a future work, we will be kind of connecting these submodules in cascaded form, and then look into the control part of it and the other complexities that are arising there. And yeah, that is the way to go forward. Thank you. And if you have further questions, please contact me at the given email IDs. And thank you for joining for my presentation.